Hello, sir. Participants கம்மியா இருக்கனால வெயிட் பண்றீங்களா?
Sir, good evening. Good evening to all. Can we start, sir, now?
Okay, sir.
So this chapter, I think this is the smallest chapter in this book. but we need to master this chapter. Then only we'll be able to tackle all the three subjects with ease. So I'll be going on some details in the basic about the kinetics, the potential energy and all. And for electrical, I will start with the formula only because it is beyond the scope of this classroom. If time permits, we'll take about the basics of electricity in another class, but we'll be starting from EI cos theta. Shall we start now? So there are two kinds of energy, major classifications, potential and kinetic energy. We'll be seeing potential energy in details. Potential energy, it's kind of potential energy, stored mechanical energy. Actually, one more question was asked for the same kind of picture. It was given in description and asked for one more, stored mechanical energy. This is stored mechanical energy. One second, sir. And product classification, we divide into potential energy and kinetic energy. This is stored mechanical energy. Chemical energy is also coming under potential energy only in the broad classification. Hydropower, this is, they term it as gravitational energy. You can see the pile driver, sir. The pile driver goes up, and then it is released. The potential energy is proportional to the height. So all of us might have seen this counterweight in a lift elevator. It serves two purposes. For smooth operation, it is required. For smooth operation, it is required, but serves one more purpose. As we go up, the motor works. The motor does. The motor is operated to lift around, for example, around 600 kg. It is lifting. The 600 kg we are going up, and it is stored in the persons who have traveled upwards. That is MGH. MGH means if 600 kg, the potential energy is, for example, if the floor is 10 floors, then the meters is 30 meters. One floor is 3 meters and 10 floors is 30 meters. So 9.81 into 600 into 30. This is the potential energy stored in all the persons who have traveled upwards. This energy we can bring it back. How? Yes, sir. This is possible. At least theoretically, this is possible. When we come down, this counterweight will go upwards so that it stores energy. Stores energy means what we have stored already in the form of mgh will be come down to the ground floor. The potential is stored in the counterweight will be in the 10th floor. And again, when again 10 persons are going up, the motor will run and it will be aided by the counterweight which will come down and lift the elevator. Partially, the motor will be loaded partially. Without this counterweight, the motor will be potentially in the form of counterweight. Sir, is there any doubt in this session? Sorry, what I told just now. Can anyone give feedback, please?
So far, okay, sir. No problem.
Okay, thank you. Yes, sir. And this thing, all these things are the lift elevator counterweight and all these things I have just added from my own experience, and it is not related with our textbooks. Okay. I'll give one example. The overhead tank is in the terrace. Let us consider it is at the height of 3 meters. You have got 100 liters of water in the ground floor, and we have to carry it to the tank. For me, with my power, I can carry 25 liters at a time and can go up to 4 times to empty the 100 liters drum kept at the ground level. So I'll be transferring the 100 liters to the overhead tank in 4 times, 4 trips. If my son carries the same, he may not carry the same weight. He may carry at 10 liters, 10 or 15 liters, 10, let us say 10 liters he can carry. So he has to travel for 10 times to deliver the same water, 100 liters. If a kid comes, it can carry only 5 liters. Then it has to walk up to 20 times to carry the 100 liters to the overhead tank. So what is the difference we are seeing? First, me, second, my son, third, a kid. The 3 persons have different capabilities, that is different power. But the energy is same. What we have stored as potential energy in the overhead tank is nothing but 100 into, that is 100 kilogram, 100 liters is 100 kilogram, 100 kilograms into 9.81 into 3. 3 is the meter height. With respect to ground, it has got a potential energy of this much. Okay. The energy stored is same, the power is different. So, can we get the power back, energy back? Is it possible? Yes, it is possible. How can we get it back? We can get a pipeline from the tank to the ground, and we can put a small turbine there, and we can generate energy from that. This is possible, at least theoretically, this is possible. But practically, for every mission, we will be having losses. So, what we get in the final stage is will be a fraction of the stored energy only. I just wanted to say what is power and energy. That's why I elaborated this. Kinetic energy. What is kinetic energy, sir? it is possessed by the moving object. Moving object, that is of mv square is the kinetic energy. This person is, and I want to put an example. I'm having a 220cc Avenger bike. At some occasions, I for stopping the vehicle to make a phone call or to wear my sunglasses, I usually stop in the highway. But usually, I don't suddenly stop. I disengage the engine and then cut off the ignition and usually I let it go on its own. It goes beyond 300 to 400 meters on its own without any fuel supply. Where this has come from, sir? This is the kinetic energy we stored while starting the bike. When we start the bike in the first gear, we usually give extra energy to move the vehicle to overcome the inertia. That energy is stored in the bike as kinetic energy. When we cut off the fuel, this stored energy is dissipated by the way of friction between the road and tires, friction between the wheel bearings, and mainly the air damping force. All these things add together to dissipate of mv square. Here I want to say one thing. See, this of mv square is the potential killer. Most of the accidents happen because we don't make it zero. The of mv square has to become zero, then only the rider will stop at the point. Of mv square doesn't dissipate in a short time. It will take its own course. So see the example, see the formula. M is the mass of the vehicle and the rider. If m is more, suppose we are going in doubles or triples, the m will increase. Once again, if the m increases, the kinetic energy also increases. Then it will be more difficult to stop the vehicle. For example, of mv square is enormous in one vehicle. Can anyone imagine which vehicle has got much m? Train has got enormous m. That's why they are unable to stop within a short span. Okay, and also the v square. Running at 40 kilometers, we can make the term of mv square zero easily. If we can keep off and m as constant k, the kinetic energy is proportional to kv square. Kv square means when we run the bike at 40 kilometers, the v square will be 1600. From 40, we go to 60. That means we are raising the speed by 50%. Then what happens? 1600 becomes 3600. It is more than double. When you raise the speed by 50%, the kinetic energy goes up to more than 200%. That is the extra petrol we have to spend. For raising the speed for just 50. For raising the speed from 40 to 60, that is increasing the speed by 50%. We have to give double the amount of petrol we are already giving. This is what information from this formula. Once again, I am detailing the power and energy. Power is the rate at which the energy is spent. Energy is the capacity available. In this example, it's the battery. Battery has got its own energy with limitations. Beyond the energy stored in the battery, we cannot deliver power. For example, if a 100 Ah battery denotes the energy stored in the battery. For example, all the batteries have 12 volt as thermal voltage by standard. If an 100 Ah battery is available with us, how much energy can it deliver? It means Ah means ampere and current. 100 Ah means it can deliver when connected to a 12 volt load 100 amps for 1 hour, or 50 amps for 2 hours, or 10 amps for 10 hours. The product should be 100. The maximum power it can deliver is 100 Ah with a terminal voltage of 12. What is the formula for power? Energy? Voltage into current into time. Voltage into current into time means voltage is 12, current the load is taking, and the time is the how long we connect the load with the battery. For example, if this 100 Ah battery is delivering to its full capacity, let's assume we will not do that. Let's assume in that case 12 into 100. 12 is voltage, Ah current into time, and 200 whatever. That is 1.2 units. 1.2 units of electricity it can save. This is how we calculate the details for the power and all for inverter and solar panels, etc. This is how we calculate. If this battery supplies a 25 watt bulb, 12 volt bulb, it will supply for certain amount of period. If we connect a bulb with 60 watts, it will deliver power for lesser time. It's 25 watt and 60 watts of power. The AH into VAH is the energy, current. Okay. One more example. We have got 1 liter of diesel. It has got a limited energy. It cannot deliver, cannot run a vehicle beyond the amount which is stored in the diesel as chemical energy. It cannot run beyond this much. What power differs. For example, a car can go up to 20 or 25 kilometers for 1 liter. Let us say assume it goes for 20 kilometers because the engine has got its own power, and for a bus the same energy, but the power is different. Power is enormous. The engine is enormous. So the 1 liter diesel can go up to 4 kilometers only. In both cases, but for both the same energy, 1 liter diesel is assumed. The energy stored in diesel is that is energy. The engines are having different powers. I think up to this point we are clear with power and energy. Can anyone give feedback, please? Power and energy. This is much essential for our subject, sir. That's why I am elaborating.
Yes, sir. It was very clear, sir. Thank you, sir.
Is it okay?
Yes, sir. Yes, sir.
Okay. Good. Power versus energy in a power plant. This is North Chennai Thermal Power Station, stage 1, situated in Chennai. The power of one unit. There are 3 units. One unit is having a power of 210 megawatt. This is the power of generator. Power is 3 units. Total power is 630 megawatt. Power is 210 megawatt. The energy generated is equal to power into time. 1 second. So, energy generated is equal to power into time. For 1 hour, the energy generated is equal to 210 into 1 is equal to 210 megawatt hour. The megawatt hour is nothing but 10 power 3 kilowatt hour. Kilowatt hour is also known as unit. For 24 hours, 210 into 24 is equal to 5040 megawatt hour. Again, add multiply by 1000, we get 50 lakhs and 40,000 kilowatt hour for units. This is nothing but 5.0 per million unit. The million unit is the common term we will be using in our subjects. Million units and billion unit. Please remember, million unit, billion unit are all the terms of energy only. This is for additional information. The peak power occurred on 29th of April 2022, 17,563 megawatt. The energy need not be on the same day, but incidentally it has come on the same day. There is no need that it should come on the same day. Maximum generation reached on the same day, 388 million units. What 1 unit of North Chennai Thermal Power Station generates is 5.0 per million units. What Tamil Nadu consumes is more than normally 320 million units. This is the peak we reached last year. It is not coming always, every day. Every day it comes around 320 to 340. The power factor. So for the power factor and the KVA, KW, and all these things, we have to take the formula only, sir. Power is VA, that is voltage into current for DC. For AC, we have to multiply it with the power factor, that is cos theta. In this triangle, the horizontal line is real power or true power. The vertical line is imaginary power or reactive power. The apparent power is the hypotenuse. We have to keep it in mind, that is KVA. KVA is the term we will be seeing in alternator and transformers. KVA into cos phi gives us the true power. That is the power consumed. The reactive power is VA sin phi. We may not be using it. In some calculation, we will be using it. For the questions will be given as real power and apparent power we may have to find the cos theta, then we will divide true power divided by apparent power and we will get cos phi. They will ask in 1 or 2 marks. May 2008, the three-phase AC load draws kilowatt of power at 400 volts and 15 amps spin point. Sir, unless otherwise they mention the voltage and current they are giving is line voltage and line current only. Calculate the power factor on the load. Sir, in the end of the session, we'll be seeing that those slides again, sir. Before that, we want to introduce some other concepts. Sir, this is the question they have asked for 6 marks. We saw this on the first session, first day. How does the industry, nation, globe benefit from energy efficiency programs? Industry, reduced energy bills, increased competitiveness. We have to keep this in mind. Otherwise, we will not be able to write so easily in the examination. It may consume time. We have to keep it in mind. Reduced energy bills, increased competitiveness, increased productivity, improved quality, increased profits. It seems all are same, but we have to keep in mind everything. For the nation, reduced energy imports. We are importing much crude oil, and we can use that foreign exchange for poverty alleviation and other things. Conservation of mine resources, improved energy security. Improved energy security, I also told on the day, I think. Can I repeat it? Okay, I'll repeat it. For India and other nations, we'll be losing our crude oil potential within 15 to 20 years. We will run out of all these things from our minds. Whereas the Gulf countries, Saudi Arabia, Venezuela, all together, the average they have got a potential for 48 years. They are more secure than us. If we conserve energy, the 15 years will go maybe up to 20 years. Let us say, for example, that is called energy security. I just wanted to throw highlight on the word energy security. Globe, reduced GHG and other emissions, maintain suitable environment. That's all. So we need to see this also. Fahrenheit to Celsius conversion. Actually, Fahrenheit, when he designed the temperature measurement, he took the freezing temperature of water as 32 degree Fahrenheit and the boiling water as 212 degree Fahrenheit. Both are same for the Celsius. 0 corresponds to 32 degree Fahrenheit, whereas 100 degree centigrade corresponds to 212 degree Fahrenheit. In between, 1 degree Celsius corresponds to 1.8 in Fahrenheit scale. That is 212 minus 32 is equal to 100. That is 1.8. The conversion we have to keep in mind. They may ask in 2 mark question also. This is one very, very important part of this slideshow. Sir. 1 calorie is 4.187 joules. Don't forget this, 1 calorie is equal to 1.187 or simply 4.2 joules. This we have to keep in mind. Specific heat is the amount of heat required to raise 1 kilogram of the substance to 1 degree. For example, 1 kg of water needs how much of energy that we can calculate using the specific heat multiplied by the temperature difference and the mass. mCp dt, the formula you might have, you might remember it. Specific heat. The specific heat is the heat we have to give to raise the substance through 1 degree centigrade. See which one is highest? Water. Water has the highest specific gravity in the list. 4,200. 4,200 joules we have to give for 1 kilogram of water to raise it from through 1 degree. Maybe it may be 28. For to raise it to 29 degree, we have to give 4,200 calories for 1 kilogram. For alcohol, it is 2,400. For lead, it is very less, 1/3. Potential energy. The bow and arrow, the slingshot, all these are stored mechanical energy. The damp power is stored the gravitational energy. Roller coaster, stored, that is also potential energy, and it will be released as kinetic energy. Kinetic energy in potential energy at the top of the mountain is having highest potential energy. This is from a different chapter, but we can answer it, sir. Tracking fixed electrical energy consumption for a rolling mill consuming 3 lakh kilowatt hour Philips electricity to produce 500 metric tons of product. This may be something 500 metric tons of iron or something, whatever it may be, consumes 3 lakhs kilowatt hour units of electricity per month and having specific electrical energy consumption of 500 kilowatt per metric ton. The 3 lakh kilowatt hour per unit, per month is the fixed energy consumption and variable energy consumption. So we have to separate it. The question I have not typed, I think. We have to calculate the fixed energy consumption. Calculate the fixed energy consumption. 3 lakh kilowatt hour, 3 lakh units is required for producing 500 metric tons. Total energy consumed is equal to fixed energy consumption plus specific energy consumption. Fixed energy consumption means, for example, the lathe is running, but it is not, we are not doing any production. Still, the lathe will be consuming some energy, no load consumption. It is like that only. Fixed energy consumption plus specific energy consumption into production. This formula gets 2 marks. $500 kilowatt hour per metric ton. Total production is 500 metric ton. And total and the consumption for production 500 into 500. From 3 lakhs, if you minus it, you will get 5,000 kilowatt hour. This 5,000 kilowatt hour is the energy it is consuming, even though it is not producing any output. Okay, sir? This is a question. This is from another chapter, but we can answer it connected to this question on the slide. One second.
Sir, they would have added, they would have got specific energy consumption as
Yes, sir,
500. They would have got the specific energy consumption as 500 kilowatt hour by metric ton per metric ton. That must be from the total energy consumption only. Where comes the fixed energy?
Yes, sir. Yes, sir.
See, generally, when you speak specific energy, total energy consumed divided by the ton
Sorry,
of GP
sir,
or what divided by the production. That is what is physical energy consumption.
Sir, have you seen any examples, sir? I'm seeing like this only in this book.
No, I worked in the foundry industry, sir.
Okay.
We whatever the unit we consume per day, we used to calculate per day or whatever it is, whatever you calculate, whole thing divided by total production. Suppose we are making 100 tons per day. If our units is 1 lakh, then it will be 1,000. Correct? 1,000 units per 1,000 units the specific unit per ton of GP we used to say. That fixed and variable and all for our calculation only. For reducing the energy consumption or towards working conservation and all, we have to think of it. But generally speaking, specific energy consumption is nothing but total energy divided by the product. Whether it is in tons, what it is in liters, what it is in gallons, whatever it is, what produce, what we suppose for if we take Ashok Leyland, we have specific energy consumption, we are calculating in terms of vehicles. So many vehicles we produce.
Okay.
That is what it should come, I think so. If I'm wrong, please correct me.
Yes, sir. I will check it up, sir, because whatever I put in the slide, I took it from our textbook only. I'll check it up, sir. I'll revert tomorrow, sir, please.
Sir, thank you, sir. Thank you.
Yes. Sir, for thermal energy, sorry, there is one Most of us are mechanical engineers, I think. Very few are only from electrical discipline. On phase change is the term we'll be using in the entire course, sir. Phase change, latent heat, sensibility, and phase change we'll be using in the entire course. The phase change is let us take example of water. Water at 0 degree, it freezes. And from 0 degree, when we add heat to that water, it is in water, still in liquid state only. From 0 to 100 degree, temperature change will be there. And beyond 100 degrees centigrade, whatever heat we give to the water will be placed only for phase change, that is water from steam. That is a phase change. And from 0 degree centigrade, when we take the heat out from that water, it will freeze. Beyond that, the temperature will be 0 only till the water fully gets converted into ice. The two phases are very important for many gadgets and all things, all these things in our subjects, sir. Because I used to say one thing. Major energy consumption in a thermal power station goes for what? Can anyone interact, sir, please? The energy contained in coal goes waste.
Waste? You mean waste?
It's a major portion.
What is the question, sir?
Yes, goes waste. We cannot recover it.
Okay, okay.
Where we lose all the energy.
Okay.
We get around 30% only major energy is lost. Where we lose.
Yes, it's exactly, yes, okay.
Sorry?
I think it's near the condenser, sir.
Yes, exactly. You are right.
Okay.
Yes. Because the phase change needs cooling of the steam to make it back to water. This is the phase change. The enormous heat we have to dissipate, and that heat goes as waste. The temperature difference is less than 78 degree, and we cannot keep that. We cannot use that outlet water for any useful purposes. We are just letting it out. In some cold countries, they are supplying it for hot water supply for homes, local homes. But we cannot. Being a hot country, we cannot. The phase change is an important plays an important role in our subject. One example, if the latent heat of fusion of water is 335 kilojoules, but we can keep it in mind also 335 kilojoules per kilogram. Determine given up by 10 kg of water at 0 degree when it freezes into ice. That means 10 kg of water is. Yes, sir. Hello. Can I continue? Can I continue, sir? Anyone,
Sir,
please?
the
Can I
background noise.
continue?
Yeah, sir. Yeah, please continue, sir.
Okay, it's only okay. I thought someone was questioning. Okay. Question is 10 kg of water is there. It is at 0 degree centigrade. Determine the quantity of latent heat given up by the 10 liters of water, take latent heat of fusion as 333 kilojoules per kilogram. We have to multiply just multiply, that's 10 kg into 335. That is 3350 kilojoules. That's all. Nothing else, sir. Okay.
Okay.
And another version, 20 kilojoules of heat is supplied to 25 kg of ice. That is 25 kilograms of ice at 0 degrees centigrade. Ice can be at 0 degrees centigrade or minus 40. Don't think that ice is always at 0 degrees centigrade. It can be at minus 20, minus 80, minus 50, minus 40 also. But the minimum, the maximum it can have is 0 degree centigrade. Beyond that, it will not be in solid state. Okay. 20 kilojoules of heat is supplied to 25 kilogram of ice. 20 kilojoules of heat is supplied. How much kilograms of ice will be melted into water? See, 20 kilojoules of heat is supplied. 25 kg ice is there. What is the mass which is getting converted into water? Once again, 20 kilojoules divided by that 335. What is the 335, sir? That is latent heat of fusion. We will get 0.06 kilogram only. Even though there is 23 kilogram of ice, we can melt only up to 0.06 kilogram. That is 60 grams of water only. Okay, sir. Very sorry, I have not put a slide.
$20 kilojoules of heat is supplied for 25 kg of water, 25 kg of ice to get water. You will get, it will melt and only 0.06 kg. That is about 60 grams of water. Ice only can become a water. The rest of the mass,
yes, sir.
Rest of the mass will be there.
Still. Yes, sir. Yes, sir.
Okay. For that, they have to fill few more joules of heat.
Yes, we have to give more. Yeah. Yes.
Okay, thank you. Got it.
Sir, I see that
these are the examples we can understand the
or,
questions, sir. This type of questions we are getting in exams, sir.
Sir, I see that 0 degrees or it is at minus 40 degrees.
Sorry?
Sir, the previous
Excuse
question,
me?
what you have said, now, sir. 25
Sorry?
kgs of ice, 25 kg of ice, you are giving
Is
20
available.
kg available. At what degree, sir? Hello.
I'll repeat the question. 25 kg of heat.
Madam, he is telling heat. 20 kilojoules of heat is given to a substance of 25 kg
How
of
many
ice.
kilograms of ice will be melted into water? That is.
Okay. They should the heat itself will have some.
We please note that nowhere we have used that 25 kg. 20 kilojoules divided by 3.
$20K divided by 335.
Yes.
That is 0.06 kg. That is nothing but 60 grams of water only you will get out of 25 kg of ice.
Yes. Okay. That is right.
Okay.
Okay, sir.
Right. Even if there is a 50 kg of ice, that is immaterial for us. Am I right, sir? We'll get one. And another term, sir, latent heat of vaporization. The quantity of heat that
Audio is
kg mass of
distorting.
liquid will absorb in going from liquid phase to water phase, or give up on going from water phase to liquid phase. The second term I told you. One second. The quantity of heat that 1 kg of mass of liquid will absorb in going from liquid phase to vapor phase, or give up in going from vapor phase to liquid phase without change in temperature is called latent
Heat.
of vaporization. That's what I told. Latent heat of vaporization. That means I told you just now, in condenser, the steam is condensed by cooling water. One example is given. The latent heat of vaporization is 2257. Approximately, we take it as 2260. When 1 kg of water at 100 degrees centigrade vaporizes from steam at 100 degrees centigrade, it absorbs 2260 kilocalories. Sorry, kilocalories, kilojoules.
Yeah.
But
Kilojoules of heat absorbs.
40 kilocalories per kilogram. That is, yes. In terms of kilocalories, it is 540. 540, we can keep it in mind easily. 540 kilocalories. Vaporization. The same principle we'll be using in heat pipes. Sir. Heat pipe, we'll be seeing it. Heat pipe is also comes in our syllabus. Sir. Heat pipe. We'll be seeing it in book 2, I think. Mechanical part. One example. Determine the quantity of heat required to vaporize 2 meter cube of water at 100 degrees centigrade. If the latent heat of vaporization of water at the temperature is 2257, that is 2257 kilojoules per kilogram. Very simple, mass into latent heat of vaporization. 2000 into 2257, which will give 4514 kilojoules. Simple, that's all. Sir, I think I am running beyond our time, I think. What's the time now, sir? Dr. Paula Morgan, are you there?
35, sir. 10:35.
Anyway, sir, I think I have covered the basics. I just wanted to throw some light into the area. You can read it yourself, the rest of the portion, and you can in just one day you can read everything in this chapter, sir. It is available. I will share it also in the WhatsApp. You just go through it, and we will discuss tomorrow. I think tomorrow there will be no class. On Monday we'll meet, sir.
What about tomorrow's class, sir? Timing?
Tomorrow class. I have to consult with others, sir. Is it okay for us to conduct? I am ready, sir.
Okay.
But many of us wanted
group,
holiday.
Sir.
Yes.
If you are fixing it,
We'll
you put it in the WhatsApp group, sir. Our group.
Okay. I'm leaving conduction convection, radiation and all, and you'll be knowing all those things. That's why I'm leaving, sir. I think I've gone on. And first law of thermodynamics, second law of thermodynamics, I think we have covered everything with this. Just read the chapter. It is not so lengthy. Read it tomorrow, and we'll discuss it tomorrow, sir. And also, from Ashok Leland, we'll discuss it tomorrow about your version, sir.
Okay, sir, sure. Okay,
Can
sir.
we leave now, sir?
Thank you.
Is it okay
Yes,
now?
sir, yes.
Thank you.
Yes, sir. Good night. Good night.
Good, sir. Thank you.
Can we end the session, sir?
Yes, please. Yes, please.
Yeah, thank you.